Hello friends, so welcome to my channel. Today we are going to discuss about the most stable electronic state of an multi-atom system, multi-electronic systems, and this is defined by ground state term symbol. Although Schrödinger equation has been perfectly solved for hydrogen atom, where only one electron is belongs, and as a result of the solution, it gives four quantum numbers, which defines the exact location or the energy of an electron within the atom. The principal quantum number, which have the integer value like 1, 2, or 3, azimuthal quantum number or orbital angular quantum number, which also values depends upon the principal quantum number. For example, n equals to 1, it have only s orbital, n equals to 2, s and p, n equals to 3, s, p, d, and so on. And in the three-dimensional, some of the orbitals have multidirectionality, and this can be explained on the basis of magnetic orbital quantum numbers, and they have subsequent orientation in different coordinates. For example, p orbital can be px, py, pz. D orbitals also subsequently have 5 orientation, and so on. Other than these three quantum numbers, electrons also can possess spin, and these spins are either upward or downwards, which is defined through either plus up or minus up. Through the solution of this Schrödinger equation, we came in position that the hydrogen atoms in its most stable condition, it having a single electron at 1s orbital. However, in case of the multi-electronic system, the electronic distribution in an atom depends upon few rules or principles. The Pauli principle or Pauli exclusion principle, which tells that in every atom, individual electrons are distinguishable. That means no two electrons can have all the four quantum numbers same. When we distribute the electrons in an atom, it gradually fill up from low energy to high energy. For example, first it will fill up 1s, then it will go to 2s, 2p, 3s, 3p, and so on. However, if there are multi-degenerate energies available, then electrons will occupy separate orbitals, and to do so, it will with the parallel spin. For example, a p2 electronic configuration, it have the two choice. Either it can paired within a single ml or magnetic quantum numbers, or it can be in a parallel. So Hund's rule is saying this parallel motion will be the ground state. Now, the above principle along with the Hund's rule although predict the exact electronic or exact energy state of different electrons, but let's take an example. If I find out the electronic structure of calcium, which have the 20 electrons in its outer orbital, so the supposed electronic configuration 1s2, 2s2, once the second quantum number field, then third. So the last two electrons will be occupied in the 3d orbital. However, the actual electrons configuration, it shows that it occupies the 4s rather than 3d. So keeping the 3d vacant, it's going to the next quantum numbers, and this happens because of the different level of penetration and shielding effect of different orbitals. So including the energies as well as the penetration and shielding power of the electrons, we came up with a simple law or regulation that electrons in a multi-electron system will follow from the lower value of n plus L to the higher value, and if more than one having the similar n plus L value, then the lower n value will be occupied. For example, 1s orbital which have n plus L 1, 2s 2, 2p 3, 3s 3. Since here in the 2p and 3s both have the n plus L value 3, but since in case of the 2p the principal quantum number is 2, which is lesser than 3, that's what it will occupy first. Now comes to the here 4s and 3d. N plus L value for the 4s is lower than the 3, and that's why the 4s orbital filled up first, and then it goes to the 3d orbitals. Now coming back to the position that an electron when resides in an atom, it can have an individual orbital angular momentum as well as it can have an spin angular momentum or spin momentum. These two are the vector quantity. Now, whenever there are two vectors persist in a single point, there should be an overlap between that one, or they will couple. For example, in an electron can have either orbital angular momentum as well as a separate spin angular momentum. Now, since these are two vector quantities, so definitely they will couple and will generate some resultant vector. Not only for the single electron, but if you have a multi-electron, for example, an atom have one electron, E1, that will have a defined orbital angular momentum and spin angular momentum. Similarly, if that atom will possess another electron, E2, which will also have a definite angular momentum and the spin angular momentum. When these two electrons resides in the same position within the same atom, there is a possibility that these two angular momentum will couple each other or they will interact each other and will generate a resultant angular momentum. Similarly, the spins will also couple and generate a overall resultant spin quantum number. Again, this resultant angular momentums again can couple, so will ultimately generate the resultant spin and orbit coupling quantum numbers. So ultimately what we are going to find that within an atom, when multi-electrons are present, there could be a different electronic energy levels are produced through this coupling of different vectors. And to solve this problem, we are coming up with term symbol. So basically the term symbol is nothing but a symbolic representation of total angular momentum, which is generated by simple coupling or interactions between the different electrons, its own individual angular momentum, and the spin multiplicity, which is again defined through the spin interaction between the different spins of electrons. And this is expressed or represented as like this, where the superscript is the spin multiplicity and the S term is the total spin, and that total spin can be obtained by sum of the individual spins from every electrons, and L is the summation of all the orbital angular momentum of individual electrons. So this L is total angular momentum, and the J is coming from the spin orbit coupling, which are also called total angular momentum quantum number, and its value is depends upon the L plus S to L minus S, all the integers values possible for that one. Now this spin multiplicity, which is as a superscript present in the term symbol, this is basically the most feasible or possible number of spin state can be find out in a multi-electron system. And the L can have the different value of integer values like 0, 1, 2 and 3 and different so on, and these are defined through the characters which are similar to the orbital. In orbital we have find out in the azimuthal quantum bar, but with a greater character. So 0 will be defined by S, 1 by P, 2 by D, 3 by F and so on. However, the electrons from a completely filled cell or subcell does not contribute to the overall term symbol, because the total orbital angular momentum of a filled cell is 0. Similarly, spin is 0. So if any atom have completely filled cell or subcell, its term symbol will be 1s0, because the spin state is singlet and also total angular momentum is 0, so it defines by 0 or S. Now take an example. Take a boron. Boron have the electronic structure 1s2, 2s2, 2p1. So 1s2 and 2s2 they are filled, so they are not contributing in the overall term symbol. So it's the p electron. So p1. So basically we can say that the electrons is reside in plus 1 state, magnetic quantum numbers. So the S or spin value is half. So there is no other spin. So total spin is just half. So the spin multiplicity is 2s plus 1, that means 2. orbitals, here is only one electron, so it belongs to the plus one, so the state is p. Now in case of the J value, because the p is 1 and s is half, so 1 plus half, that means 3 by 2, and 1 minus half, half. So these are also just one unit difference, so there is no middle part, so only 3 by 2 and half. So the term symbol can be possible from here is, depending upon this type of representation, 2p, and there are 2 J value, 1 by 2 and 3 by 2. So one of these will be ground state term symbol. Now for defining the ground state term symbol, we find the Hund's rule, which expresses that the highest S value or spin multiple value will be the ground state always. But if we have a multiple energy state which have the same spin multiplicity, then we look at the highest orbital multiplicity or the overall angular momentum value. And finally, we look at the J value, that means spin orbit coupling value. And for the less than half filled orbitals, the lowest J value is the ground state. And for more than half filled value, the highest J value is the ground state. Now for this boron, which have only one p electron, and we have found that there are two possible term symbol within this configuration. So since this is then less than half filled, therefore lowest J value is the ground state, that means L minus S. So here L minus S is half, therefore the ground state term symbol is 2p half. Take another example, carbon, which have now 2 electrons in its valence orbital. So these 2 electrons can be distributed in different way. For example, in a parallel motion, or like opposite orientation where the orbitals are different but the spins are changed, and another thing, they can couple, right? But if I consider the Hund's rule, so among these three, this will be the ground state because they will possess the parallel spin, since all these orbitals are degenerate. Therefore, if we calculate the term symbol for this one, so the total spin, because this is half, so total is 1, so spin multiplicity is 3. Now orbital, so this is plus 1 and this is 0, so total is 1, therefore the state is p. Now J value, if I consider p plus, that means L plus S, 2L minus S. So L plus S means 2, L minus S means 0, so there is another integer 1, so 2, 1 and 0. So there are possible 3 energy state. All the multiplicities are 3. So 3, the term is p, only J value is differ. So 2, 1, 0. However, these electronic states, although they are not the ground state, but they can also generate the term symbol which are higher in energy. Now comes to the lower energy part, since this is the maximum spin multiplicity and since this is half filled, so the ground state term definitely will where the J value is the lowest. So 3p0 is the ground state term symbol for the carbon. Now come to some basic points. How exactly will follow through to get a stable term symbol or ground state term symbol? First things, what we have to do, we have to distribute the electrons, and we'll distribute from the highest ml value. For example, in the p orbital, we'll start from the plus 1, then 0, then minus 1. And a full or cell or subcell do not contribute to the overall angular moment, so we will not consider the full cell or subcell. Now next things, we'll calculate the overall spin value by summarizing all the possible spins from the individual electrons, and then we'll calculate overall angular momentum by summing all the individual angular momentums, and then we'll calculate J value from L plus S to L minus S. All the integers are possible, and we'll find out if the system is half filled, less than half filled, then L minus S is the ground state. If it is more than half filled, L plus S is the ground state. If it is exactly half filled, then J will be S value, because in that case L value is 0. Now take some examples. Fluorine, which have the valence orbital p5, therefore the electronic distribution will be in this way. So the total spin because individually plus half minus half, plus half minus half, plus half, so ultimately half. So the spin multiplicity is 2. Now come to the orbitals. The 1 plus 1 plus 0 plus 0 plus minus 1. So ultimately get 1. So the state is P. Now comes to the J value. Since the P L value is 1 and the spin is half, so it will have again 3 by 2 and half. But since the system is more than half filled, therefore higher J value is the ground state. Therefore the ground state term is 2P 3 by 2. Let's take a D3 system. In the D3 system, the 3 electron will be distributed from the higher ML value gradually, and according to the Hund's rule, they will be in the parallel spin. So the total spin is, since all are parallel spin, so together is 3 by 2. Therefore, the spin multiplicity is 2 into 3 by 2 plus 1. So 4. Total L value plus 2 plus 1, 0. So 3. 3 means F. Now the J value 3 plus 3 by 2 to 3 minus 3 by 2. All the integer values are possible. Therefore 9 by 2, 7 by 2, 5 by 2 and 3 by 2. Since this is less than half filled, therefore the lowest J value will be the ground state. Therefore the ground state term is 4F 3 by 2. Now the most important application of this term symbol will get in the electronic spectra. That means when defining the electronic spectra, what are the variable adsorption or emission lines are possible in an atomic spectra can be easily calculated theoretically through the prediction of term symbol. And now for the electronic spectra, we have to calculate all the possible term symbol, either it is ground state or excited state. So in our subsequent video, when we'll define the atomic spectra, we'll define how to calculate the various excited state term symbol and how to define the various possible transition between the electronic structure. So thank you for listening, and if you really like the video, please subscribe my channel and don't forget to press the bell. And if you have still any queries or suggestion, please don't forget to email me. Thank you. Thank you very much.